All right. I know that's enough of that. I know. I'm just so excited to be doing the calculus. You know what I'm saying? We're talking about limits. Everything is great. Okay, so on the last video, we left off right here where we discovered that the limit as x approaches 2 of x squared is equal to 4. Okay. And we discovered that by getting x closer and closer and closer to 2 from the left, and closer and closer and closer and closer to 2 from the right. And if you remember this blue dot coming along the function here, getting closer and closer, its behavior, its value was getting closer and closer to 4, whether we came from the right or from the left. When we came from the left, it was approaching 4 from below. When we came from the right to x, the value of the function was approaching 4 from above, because it was coming J-Sean, down, 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 down. Okay, so that leads us to, and well, hopefully you might be thinking, hey, Mr. B, this is easy. Again, all I do is I replace x with 2. 2 squared is 4. It's substitution. What's the big deal? Very simple. Well, sometimes it is that simple, but a lot of times it is not. Okay. All right, so bear with me because we need an informal definition of a limit, because that's all we need for this course. So let's follow along here. Okay, very important that you have this conceptual understanding. So don't zone out. If the function f of x can be made as close as we like to some real number a. All right, hold on. We need an example. Remember the previous example there, f of x equals x squared. Okay? And what was our example? We were finding the limit as x approaches 2 of x squared. And we found that that was equal to 4. Well, guess what? That is the a that we're talking about, the capital A. Okay? F of x was getting closer, the value of the function was getting closer and closer to 4. Can be made as close to some real a by making x sufficiently close to, but not equal to, little a. Okay, so our little a was the 2. And along the x-axis here, this was our little a. I took another screenshot. In this case, this is the screenshot of x approaching from the right. From the right. It's going left, which means it's coming from the right. Okay, so this is my little a right here. In our case, it was 2. Then we say that f of x has a limit of a as x approaches a limit of capital A, I should say, as x approaches little a. Capital A was 4, little a was 2. And we write the limit as x approaches little a of f of x is equal to capital A. In this case, f of x is said to converge to a as x approaches a. Convergence. That becomes very important in later mathematics. Okay, if that sounds confusing, don't worry. I'm going to try and help you out here, maybe with a little bit simpler concept here. Me personally, I like to think of the limit as the behavior of a function, f of x, as x approaches a particular number a. What the heck is the function doing? Where is it going? Or basically, what is its value? What is the value of the function right around the x value in question? The x value we use theoretically to be a. And again, before it was specifically 2. Okay. Well, as this function if you think of this blue dot as moving down this curve, this blue line was moving closer and closer and closer to a. What was the behavior of the function? What was the value? Well, the value was 4. And the same thing as when it was coming from the left, moving right. Coming from the left, The dot was moving up this curve and getting closer and closer to 4. The behavior of the function, where's it going, what is it doing, what's its value? That's what we're really concerned with. Okay. Now, some very, very important stuff here. When we define the limit of f as approaches a, x does not reach a. It does not reach a. It gets closer and closer and closer. I think I've given you the example of some guy walking towards a wall, right? If this dude goes halfway to the wall, every time, theoretically, he will never, ever, ever get to the wall. It's the same sort of thinking. The limit is defined for x close to, but not equal to a. So in our previous example, we were finding the value of the function as x got very, very, very close to 2, but it never equaled 2. Okay? But Mr. Becker, 2 squared is 4. I know. Sometimes we can use that to find the limit, but that's not how it's defined. It's defined as the behavior of the function as we get closer and closer to that particular x value, which we just say is a, some arbitrary value a. Whether the function, here's another important point, whether the function f is defined or not at x equals a is not important to the definition of the limit of f as x approaches a. What the heck does that mean? Well, look at this function right here. If we wish to find the limit as x approaches 0, we would have a 0 in the denominator, and that is undefined, boys and girls. We can't divide by 0. The world will end. Okay, but as far as a limit is concerned, it's not important because we're not asking what is the value when x equals 0. We're saying what's happening to the function as x gets closer to 0. So here's a case where we could not use substitution. We could not replace x with 0 because we would get something that makes no sense, 0 over 0. So what do? Okay, well, if you look at the graph, this is the graph of f of x equals 5x plus x squared over x. Mr. B, it's a line. What up with that? Well, I'll show you that in just a second, but if you notice right here we have, or recall, we have a hole in the graph because when x equals 0, the function is undefined, and that's how we represent it. Well, how in the world could it be undefined? Well, let's manipulate this algebraically a little bit. I think you'll agree that this is equal to x times 5 plus x over x. What did I do? I factored out an x. And these cancel, and I'm left with 5 plus x. So this is the graph of the line y equals 5 plus x. It's just the original function is undefined at 0. Okay? So now we could substitute in here, and we can say that the limit as x approaches 0 of 5 plus x is equal to 5 plus 0, and then I can now use direct substitution because it's not undefined, and that is equal to 5, which makes sense because approaching from the left and from the right, in other words, as x approaches 0 from the left and it approaches 0 from the right, the value of the function approaches 5, and that's what the definition of a limit is. Okay, time for a couple of examples, and you're going to think, wow, you could have just gone right here because this is going to be very simple. But you have to understand the underlying concepts of limits, or the rest of your journey is going to be very difficult. So A, the limit of as x approaches 2 of x squared, or you could say the limit is x squared as of x squared as x approaches 2. First thing you should do, can I use direct substitution? Can I replace x with 2? Anything bad going to happen? Is the function undefined? And the answer is no. We know that the limit as x approaches 2 of x squared is equal to 2 squared, which is equal to 4. Okay. What about b? Okay. Well, I cannot replace x with 0 because I would have something undefined. So this would equal the limit as x approaches 0. Don't forget to write the limit as x approaches 0, otherwise it's wrong. I can factor out an x times x plus 3 and put that over x. Yippee-ki-yay, the x's cancel, so this equals the limit as x approaches 0 of x plus 3, which equals, now I can use direct substitution because it's not undefined when I substitute. 0 plus 3, which is equal to 3. Okay? And we will graph this in class to show you. In fact, I want you to take your calculator out after this and graph f of x equals x squared plus 3x over x. And you'll see that as x approaches 0, the graph is approaching the y-axis right at 3. What about this one? C. Okay. Well, if I replace x with 3, I'm going to get 0 in the denominator. So hopefully I'm going to be able to factor, which I can, the difference of 2 squares. So this equals the limit as x approaches 3. X squared minus 9 factors into x plus 3 times x minus 3 over x minus 3. Isn't this fantastic? Kapow theorem. Yoo-hoo! So this equals the limit as x approaches 3 of, what are we left with? X plus 3. Okay, and now I can use direct substitution because nothing is undefined. So that's 3 plus 3, which is equal to 6. Okay, and I want you to graph this on your calculator, and we'll do it in class as well, to see what the graph looks like around x equal to 3, or as x gets closer and closer to 3. All right, that is it. I hope you enjoyed it. I am beyond excited. We have taken our first baby steps. Congratulations. See ya!